One point about the crust that is quite important is that not only does it cover the entire surface of the Earth, but it's also not a solid layer. The crust is actually broken into several individual pieces that we call plates. Now, the theory of plate tectonics, which we have heard about since we were all in grade school, is that these plates that make up the Earth's crust don't stay in place. Rather, they shift positions across the Earth's surface over time. And part of this came from the realization that if you put South America and Africa together, they actually fit quite nicely together. And if you look at the theory of plate tectonics and rewind the clock, go back in time millions of years, then all of these land masses would fit together quite nicely in a single large landmass, which we call Pangaea. Now, the original concept of plate tectonics came about in the late 1800s. That concept was known as continental drift. Just a historical note, continental drift, when it first came out, when the idea first came out, was kind of a joke. A lot of people thought it was a really bad idea, bad theory. It wasn't until early 1900s that really the evidences of continental drift became real, and we have what we know today as the theory of plate tectonics, which turns out to be correct. Now, how do we know about the movement of the crust plates? Well, one of the largest bits of evidence is from the Earth's magnetic field itself. Recall that magnetite is formed when you have lava on the surface of the Earth. Then as it cools, it crystallizes into igneous rock. But the poles of the individual magnetite molecules align themselves with the Earth's magnetic field, and then they're locked into position and they become magnets. Well, you pile up enough of these layers of lava, you get these different layers of magnetite, or this igneous rock, which basically acts as a record book of the Earth's magnetic field. And you can look through these layers, and what we've seen is that the Earth's magnetic field varies in strength and direction over time. One very big important note is that the magnetic field has actually reversed direction 22 times over the past 4.5 million years. And there are some theories that say we're due for another reversal. Well, we'll have to see about that one. But the reason that this is important is that the magnetic field can help, the record of the magnetic field embedded in the igneous rocks can help us identify where the plate was located, as well as what time period those igneous rocks were formed. So we get a map of when and where the plates were. And if we look through the record, sure enough, the magnetic fields show that they were closer together longer. Like if we took the magnetite in South America and in Africa and mapped them together, they were more identical many years ago, and now they are more different, showing that sure enough, millions of years ago, the land masses were closer together. Another bit of evidence that we have for plate tectonics is from the ocean itself. When we were able to actually map out the bottom of the ocean floor, we found there were oceanic ridges and oceanic trenches. A ridge is basically a mountain range at the bottom of the ocean floor, and a trench would be basically a valley. Now, these oceanic ridges, tend to coincide with earthquakes that happen in submarine areas, that is, below the Earth's surface, in the crust beneath the ocean. And one of the areas where we see the most number of earthquakes is right along this line here, the Mid-Atlantic Ridge going right through the center of the Atlantic. One of the largest mountain ranges, one of the largest submarine mountain ranges. And so the fact that there's so many earthquakes tells us there's something going on right there along that line, which we'll address in just a little bit. Oceanic trenches are long, narrow, deep troughs with very steep sides that seem to run parallel to continental edges. So we could see some trenches right here, right along the edges of all these continents. Now, here's the idea of why these ocean ridges and trenches tell us so much about plate tectonics. What's happening with these ridges is hot molten rock comes up from the Earth's interior, from the mantle, and emerges, turns into lava right along this rift. And the lava will build up, and you've got yourself a mountain range at the bottom of the ocean floor. But it's going to flow out from this mid-Atlantic ridge, and it's going to flow out in both directions. Excuse me, those are a couple bad arrows. Let me try a little better. There we go. So it flows out in both directions. Now, here's a really interesting result of this. If you were to go and evaluate the types of rock at the bottom of the ocean floor, what you would see is more of an igneous type of rock here along the ridge with a very small sediment layer on top of that. But as you go further out, say out here by the continents, you're going to see that the sediment layer is thicker, much, much thicker, which means that there's been time for not only for the igneous rocks to break down and become sediment rocks, but also for other marine life to, when it dies, to settle down to the bottom of the ocean and pile up. So you've got much thicker sediments, which indicates that the regions nearer the continents are much older. But the region right near the mid-Atlantic ridge is newer. It's a newer landmass. So we're forming more land masses as the magma emerges. Okay, so newer land, middle of the ocean, so what? Well, as this magma comes up, not only does it spread side to side, but it takes the entire plates and it pushes them apart from each other. That's where the plate tectonics comes in. As the magma comes up, it pushes the plates away from each other. Another bit of evidence on the bottom of the seafloor is the magnetic field recorded in rocks there. Basically, you have paleomagnetic patterns of magnetic strips in the ocean floor. So you have patterns as the magma cools and forms into igneous rocks, you have patterns of magnetic field that are identical but opposite directions because of the flow of the lava. They're identical on either side of the rift. And then as you have a new layer form, you have more identical magnetic strips. And then, so you have these older layers which have identical properties, and then more newer layers which have different but identical properties to each other. Now, these patterns match the patterns found elsewhere around the Earth, as we saw a couple slides ago, talking about the magnetite that forms on the surface of continents. These patterns match those quite well, and so they help us to determine the age of the ocean floor in certain locations. They help us to indicate how quickly the seafloor is spreading.